Thank you so much for coming to the session number 8 of Vadodara AI Meetup. My name is Krunal and he is my colleague Bhavik. So today we are going to talk about RAG and GraphRAG and how we move from vector-based retrieval to the relationship-aware reasoning. Okay, let's give some time to settle down the audience first. Okay. So before we start, I just want to understand the audience, like how many of you are hearing the word RAG for the very first time? Please raise your hand. Okay. How many of you have used RAG in production? Okay. And how many of you are familiar with GraphRAG? Okay. Cool. Thank you so much. So this is the session agenda. We are going to talk about why LLM needs external knowledge, what is RAG, retrieval augmented generation, how does it work. We'll have quick demo of basic and advanced RAG, and we'll talk about where the traditional RAG struggles, how GraphRAG solves that problem, about a demo about GraphRAG, and at the end we'll also discuss which one we should use one over the other. Okay, so you guys came here to learn about RAG, and this is the first slide, like RAG is dead. So what's going on here? People who are reading the latest news in AI topics might have heard about this statement. Whenever the context window gets bigger and bigger, people talk that okay, RAG is dead. We no longer need RAG. But we'll find out in today's talk, like, is it even worth learning about RAG today, or we can skip this topic entirely? So let's discuss, like, why do we even need RAG in the first place? So the LLM knowledge is static. They have a knowledge cutoff which is 6 to 8 months old, and they are not aware about the enterprise information. They don't know the terabytes of enterprise data. They are not trained on those information. So if you do the Q&A around it, you're not going to get the answers. And that enterprise data also keeps getting changed over the period of time. And the users who are asking questions, they are basically looking for the exact information, exact answer of the question that they ask. So the traditional LLM cannot produce the answer of the question if the question is around the enterprise data on which they haven't been trained. Like if you go and ask that, okay, what is our internal company policy say about the remote work? So the LLMs don't know in which company you are working. They are not aware about the policies of the company. So obviously they are either going to hallucinate or they are going to tell you that, okay, they don't have the information. So back in the day, there were a couple of techniques that have been tried. Like one of them is fine tuning. Fine tuning is like training your LLM on the top of enterprise data, which is an expensive process and it's not scalable because, as I mentioned before, that the enterprise data keeps getting changed over the period of time. And if the data changes, then you will have to retrain the LLM again. And that's why, like, it's an expensive process. It's not a scalable. Then context stuffing. So as I mentioned before, like when the context window gets bigger, like the frontier model has million token context window these days, and people start talking that, okay, RAG is dead. We no longer need RAG because we can feed that entire information into the context and we can get the answer. But the people and who are actively using the AI, and the research also says that when you start putting entire information into the context window, if your information is somewhere in the middle of the context, it's either the LLM is either not gonna give the exact answer to you around that information, or it's gonna hallucinate, because people are still struggling with context window when the context window reaches to 60-70%, and RAG reduces this noise actually. And there are also some manual rules that people tried back in the day, which is again not scalable. So the scalable and cost-effective solution over here is RAG. Let's understand how RAG works basically. So there are two steps. First thing is, like, you have to insert your enterprise information into the database so that when a user is asking question, we retrieve the relevant information from the database, feed into the context window, so the LLM can answer the question around that. So this is the data ingestion pipeline. Like you have enterprise data in terms of document, PDF. You can also have video, audio, markdown files, whatnot. Some of them needs pre-processing, not all data needs that. And the first step that you go through is the chunking. So you split your entire data into a number of chunks because LLM has again like limited context window. The embedding model has limits. So you chunk your entire information. Once the chunking is done, so let's say if you have 100-page PDF, you are chunking that into 1-page PDF. And then you feed that chunk into the embedding model. So the embedding model generates the vectorial representation of that chunk. So they just generate some sort of mathematical numbers. That numbers you feed into the database, you index them, and then they become ready for the Q&A. So once the data has been inserted, then the retrieval part comes. Like when user asks question, you generate the embedding, you retrieve the similar embeddings from the system, you feed that chunk respect to that embedding into the prompt, and you send it to the LLM. So this is the RAG part actually. RAG means you are retrieving the relevant information from the vector databases, that is retrieval. Augment is like stuffing that relevant chunk into the prompt, that is the augmentation part, and you send that entire prompt with chunk to the LLM, that is the generation part. So this is the RAG pipeline looks like you retrieve, you augment, and then you send it to the LLM for the generation. So these are the core components as we discussed, like we have data ingestion step, then chunking, embedding, vector DB, retrieval, and the prompt assembly. That is the augmentation thing. So let's talk a bit about chunking. So back in the day when RAG came into the picture, a lot of people were not aware about the best practices. They started with fixed size chunking, and for the fixed size, they started with 500 or 512 number of tokens. They split that document into that tokens, and they had a bit of overlap so they can able to connect the chunks. But over the period, the chunking strategy evolved. People started using sliding window, recursive chunking, then there were semantic chunking and the parent-child chunking as well. In the semantic chunking, you give the embedding model, you give the doc, it will generate the embeddings, and the embeddings that are similar in nature, it will group them and keep that under a single chunk. So that's why you have contextual chunking generated as a part of that. And in case of parent-child, you are generating small child chunks, and you group similar child chunks under a single parent, and the retrieval happens on the child chunk. But when you want to feed that context to the LLM, instead of sending the child chunk, you send the parent chunk. So you give the bigger context so the LLM can answer better questions. So that's how like chunking is very important, because if you have better chunking, you have better context and you are able to get better answers through LLM. And this is how embedding looks like you have this text words over here. You feed those words into the embedding model, and they generate the vector representation. So you can see that car and vehicle, they are similar in nature. So they have similar vectors, but the pizza is completely different. So the vector representation of pizza is different. And you can also see that in the vector space, car and vehicle will be very close to each other, versus pizza will be far apart. So the distance between the vector determines how similar those chunk and those informations are. So how does this work basically? So we are, in case of RAG, we try to retrieve the semantic, we do the semantic search basically, and we try to retrieve the word which are similar in nature. And there are different methods, like you have cosine similarity that this modern vector databases use to retrieve the similar chunk from the vector DB. There are two other methods as well, like Euclidean distance and dot product. So the cosine similarity measures the angle between the vector to find the similar vectors. The dot product measures the angle as well as the magnitude, like how long the vector is, to find the similarity. And Euclidean distance calculate the distance between the vector. So if we have a query around car insurance and the document mentions about vehicle insurance policy, so that isn't quite in the similarity matrix, that is very high. But if you ask about the car insurance and if your document has pizza recipe, so the similarity is very low. So we are not exactly matching word to word, we are finding similar words in nature, and we are doing similarity search in vector DB. And as we discussed before, like we have this cosine similarity, we have this dot product and Euclidean distance for the similarity computation. So the user's question first gets embedded, and once the embedding is done, we do the similarity search and we retrieve the top k chunks. Once you have those chunks, you feed them into the prompt like this way, that you are an assistant, answer only using provided context. If you don't know the answer, just say that you don't know. And you give all the chunks that you have filtered in similarity search and feed it over here. So this is the winning part. Like when you have a long context window, instead of putting entire PDF 100 page PDF, you just feed the relevant information and remove the entire noise. And if you just feed the required information that is associated with the question, you are gonna get very good answers through LLM. So this is the winning part of RAG. We'll quickly see the live demo of the basic RAG that we have in place. This one is that. Okay, so the text are visible, right? Or should I zoom in more? Now? Okay. So we are using LangChain over here as an orchestration framework, and it has a lot of built-in methods around chunking and embedding. So as you can see over here, that for the chunking, we are using this character text splitter for fixed size chunking and recursive character text splitter for recursive chunking. And for the semantic chunking, we are using this semantic chunker. This OpenAI embeddings is we are using for the embedding purposes, and chat OpenAI we are using for doing the Q&A. And we are using ChromaDB over here for storing the vectors. So I'll just quickly run this. These are nothing but just simple imports over here. Then here we are using the GPT 5.4 as an LLM. So that's why we have this OpenAI API key. The embedding model we are using is around this text embedding 3 large. This is again from OpenAI. And the dimension of this embedding is 3072. You can change this, but it's up to you, like how many dimensions you want to keep. So this 3072 will represent the length of your vector. So when you do the embedding, it will generate the vectors, and each vector will have 3072 elements in it. So this is associated with that dimension. The chunk size is 512, and we are doing 50 chunk overlap. And now we are initializing the OpenAI over here. We are initializing the ChromaDB, and we are also initializing the embeddings. So these are nothing but plain Python functions. We are loading the PDF. We are validating whether it is empty or not. Then this is the chunking part. So in the fixed size chunking, we are using this character text splitter, and we are defining that, okay, this is the chunk size that you should split the document into, and this is the chunk overlap. So based on this chunk size, it will split the entire document that we pass to it. Then we have recursive character text splitter. So it will also follow the same pattern, but for the splitting the document, it is gonna use the multiple separators over here that we define. You can define any other separator. It's up to you which separator you want to use, but it is it will use this separator to split the document. Then we have semantic chunking. So in semantic chunking, we are defining the embedding model, and we are also defining the threshold. So if the chunk matches, if the embedding has greater than 95% similarity, we should keep them under a single chunk. And this is again the sentence splitter that we are using. So if the similarity threshold is below 95, it's gonna put that into a separate chunk. So this is how we are gonna do the semantic chunking. Then we have agentic chunking as well. You can also use LLM to do the chunking. So here we have this prompt that split the following text into the coherent chunks for retrieval and return only the JSON. And we are also mentioning that each chunk should be 150 to 400 words. So if you have good budget, you can also opt for the LLM based chunking. And we have this drop down in the UI. So that's why we are we have these different chunking strategies in place. Then here we have these two functions. One is around creating the vector store, and the another is around retrieving the documents from the vector store. Then for the similarity search, we are directly doing the similarity search on top of vector store. So whatever query will comes in, so this will internally generate the embeddings, and it will compare the embeddings and return us the chunk which are similar in nature. So this is the advantage of using the orchestration framework over here. Then we are creating this Q&A stuff, like we are mentioning this is the prompt, that you are an helpful assistant answering the question based on the provided context, and use only the information from the context to answer. And if you don't know, just say that you don't have the information to provide the answer. And this is just formatting purposes. Some methods are around that. And for the generating answer, we are going to call the LLM over here to generate the answer. And whatever the answer comes in, we'll just send it to the end user. And this is nothing but the initialization of the global variables. So this is the processing part. Like when you do the data ingestion, you load the PDF first, and then you apply the chunking strategy. So chunking strategy will come from the UI. Whatever chunking strategy user selects, we will send that into this function, and the function that we saw before, which has 4 chunking strategies. So it's gonna do the chunking based on the strategy that we specify. And here I'm printing some chunks, so you will be seeing that how that looks like. And once that chunking is done, we also send those chunking into the vector DB to store it. And then we are also gonna see some sort of vector, like how the vector around that chunk looks like. And then when we ask a question, we initiate the similarity retriever, and we retrieve the document, we retrieve the chunks from it, and then we call the generate answer. So the generate answer will do the LLM call. Similarity retriever will retrieve the similar chunks from the question, and we'll see that in action in a while. So this is the Gradio app that I have created. It's a big scrolling. Oops. Yeah. And now I'm launching the GraphRAG. So I have one PDF. I'll show the PDF in a while to you. And I'm going to use the semantic chunking over here to process it. So by the time this is processed, I'll show you the PDF. So I have this Meridian Technologies handbook generated HR policy. This is a fake document generated through LLM, and it has bunch of information. So we are gonna query around this office locations, and once the doc is processed, so since we are doing semantic chunking, it's gonna take some time because it will first generate the embeddings, it will group the embeddings which are similar in nature, and then it will give you the chunks. So we have this 49 chunk, and we will quickly see that chunk as well. So these are the chunk. The first chunk has 125 characters. These are the metadata around it. The second chunk has 85 characters. So again, these are grouped compared to how they are similar in nature. And then these are the third chunk, which has 309 characters, and fourth chunk has 679. And these are the vector representation over here. So you can see that this is the, this is the first representation of vector of first chunk. So there are 3072 dimensions. So this is the this is the first chunk, which has 125 characters, and this is the vector representation of that chunk. So this is how the embedding model returns us the information. And when we go and ask about this office locations, so it's gonna find through that chunk, and it will tell us that, okay, these are the office locations, and we can validate that there are 6 locations over here: Austin, San Francisco, New York, London, Singapore, and Toronto. So this is the example of RAG, like how does it work under the hood. But again, this is good for POC because this does not have the advanced concept that actually improves the overall quality. So as we saw, the basic RAG works, but you cannot use that in production, because if you start using that in production, you will see that it's not answering a lot of questions, because that is lacking the advanced concept which further improves the accuracy of the RAG. So if you want to implement something around this in the production, then you can use below common techniques that are widely available as a best practices around creating RAG application for production environment. So one of them is hybrid search. Hybrid search is the combination of keyword search and semantic search. So the semantic search we discussed, like it will do the similarity search, find the similar vector from the database. The keyword search will do the exact keyword matching in the database. So why does this two improve the accuracy? Because these two complement each other, and one is overcoming the problem of the other. So if you have a document which mentions around Python and also talks about Snake. So if you ask a question, since these two are similar in nature, you will probably have a chance that if you ask of the best practices around Python, you might get a chunk which talks about Snake, because those two are similar in nature. So in that type of scenario, keyword search helps us, because keyword search improves the accuracy by doing the exact keyword searching in the chunk, and the vector search will give you probably wrong results in that case. But if you want to do the similarity search, if you want to find the similar information, in that case, keyword search will not be able to provide the good answer. So in case of hybrid search, since this is a combination, you can tweak this as per the fractional ratio. So for example, you can give 60% weightage to similarity search and 40% weightage to keyword search. And if you want to do the keyword heavy search, you can again go for 70-80% of keyword search and 20% for similarity search. Then there are re-ranking models. So re-ranking models, basically what they do, once you retrieve the chunks and send it to the re-ranking model, they are cross-encoder model, and they give the relevancy score to each chunk, how relevant that chunk is for the given question. And it will also sort the chunks into the relevancy score. So the higher relevancy score will be at the top. And when you send that information to the LLM, it will give you good answer, because the chunk which has most likely the answer of the user's question will be at the top, and LLM will be able to process it. It will be able to give the proper attention and give you the good answer. So that also improves the quality of the answer. Then we can also add additional metadata filtering. We have seen like we can generate bunch of metadata once you do the file processing, and then you can apply the metadata filtering as well. You have query rewriting. So as a part of asking follow-up questions, we usually just mention, we do not specify the entire question properly. We just mention it with the reference of the previous question. So the query rewriting helps us. We, based on the previous thread of the history, we reformat the query so that we are able to retrieve the proper chunks from the database. We also have the demo around this advanced, so we'll quickly go through that too. So we are using this BM25, best matching 25 algorithm here for keyword search, and we are using Cohere for re-ranking. So we have implemented two things in place. One is hybrid search and another is re-ranking model. So here we are initializing the Cohere API key. So it's just an API call. You just have to have the API key for that. And once you have the API key, you can send it to the model and they will do the re-ranking on your behalf. So this is the hybrid retriever, and we can see that when we call the retrieve method, the first thing we are doing is we are finding the similar documents from the vector. So we are first doing the similarity search. And then we have the keyword search. So before merging the two, we are normalizing the score, because they both will have score of different dimensions. And here, based on the alpha defines the weightage, like how much weightage you want to give to the similarity search and how much weightage you want to give to the vector search. So whatever score we have, we multiply that with alpha for the similarity, and for the keyword, we subtract that alpha from 1. So this is how the weightage can be calculated. So if you want to give the weightage to similarity as 60%, so similarity will be 60% and BM25 keyword matching will be 40%. And once you have the score calculation, then at the end you combine the score first, similarity search score and the keyword search score, and then at the end you sort them in the order so that higher score will become at the top. And in the cohere re-ranking model, we are calling this cohere client and the re-rank method, so that we can get the proper relevant document in the respective order from the cross encoder model. So these two things we have in place for advanced RAG. And again, this processing part is same, like you can select the chunking strategy based on the given chunking strategy in place. We have 4 chunking strategy. And once the chunking strategy is done, you go to the vector DB, you create the vector, store them. And when the question is asked, we first do the hybrid retrieval, and we are defining the alpha as 0.6, which means we are giving 60% weightage to semantic search and 40% weightage to keyword search. And once that retrieval is done, we send it to the re-ranker model, and after that we generate the answer over here. So this is again very similar and simple to implement, but this significantly improves the quality of the user's question. So this is another Gradio app that I have created for the advanced RAG. And now we will launch this advanced RAG 7863. So the UI is similar. First, we will do the data ingestion part. Again, we will feed the same PDF into it. And this time we are going to use the recursive chunking strategy, and it is very fast because you don't need to generate any embeddings over here. And this time we will query around the salary. So there are different titles and there are salary range associated with different titles. So we will go and ask, what are the salary range associated with different title? And this will retrieve that salary range, and we can quickly validate that too. So oops. So here we have salary range for analyst is 55 to 85, which is exactly mentioned in this PDF document. So that's how the RAG works under the hood. But RAG also has its limitation. Like it works well with query like this, that if you ask what are the side effects of drug X, it will gonna fetch the proper content and it will gonna give you the answer. But if you ask a question something like this, that why drug X is discontinued in the US but not in the, in the Europe but not in the US, then probably you will get either half answer or you will, the LLM will hallucinate. It will not give you the exact answer that you are looking for. So there are some failure patterns that are associated with RAG architecture. One of them is fragmented knowledge. So the document that we upload, the document, one single document will not have the full answer. Like you will have multiple documents, and if you ask a question, so the answer could be coming from multiple docs. So if you want to know that what is the reason about company revenue drop, and one document talks about that company revenue drop because of a CEO change, and the another document talks about that new CEO introduced the cost cutting in place. So if you ask a question, and it will probably do the similarity search, and it will give you the answer that okay, the CEO change is the reason about the revenue drop in the company. So the RAG is not able to connect the cause and the effect over here because that information is spreaded into multiple documents. Then it doesn't, it's not aware about the relationship. Like if RAG doesn't know which element is connected to what element, and if you ask the question like which supplier are indirectly impacted by the new company policy, so this needs a graph traversal. The RAG will not be able to identify the content accordingly from the system because it will do the similarity search. It will not be able to traverse through the doc, and it will not be able to connect the information. Then this is the third pattern, like multi-hop reasoning. So you have one chunk which is associated with the other chunk, and then it is further associated with the third chunk. So if question comes around this, like which customers are affected by the chip shortages at supplier X, So your one document talks about that supplier X supplies chips to manufacturer Y. Manufacturer Y builds components for product Z, and product Z is sold to customer W. So when you ask a question, and RAG will try to find similarity search based on the similarity search information around supplier X and the customer. It will completely miss the connection over here, and it will not be able to connect this entire knowledge like this are the complete order one after the other, and it will probably give you the half answer, or it will most likely again hallucinates. So why does this happen? So this happens because of the underneath architecture of the rack. Like when we do the chunking, we are splitting the context into multiple chunks, and even if you have multiple dogs, so the context is further splitted. The retrieval is flat, like you are just doing the similarity search. You are not traversing through any graph, or you are not connecting the knowledge of different vectors. And you just do the similarity search, like they are good for sounds like this, but they are not good for connected to this. And again, the retrieval, every time retrieval is flat, like it's not, there is no persistence, some sort of connected information through which you can traverse and find the answers. So RAG is really good if you want to do the similarity search type of queries, but if you want to connect, if your questions has connected knowledge, then it's gonna struggle. So how do we move from retrieving text to understanding knowledge? So this is where GraphRAG helps. And now I'll hand it over to Bhavik. He will give us a walkthrough of GraphRAG. Thank you.
Thank you, Krunal. Hello, everyone. Myself, Bhavik, and I'm going to cover the GraphRAG part. So everything Krunal covered so far, the RAG, any technique that he has covered, chunking strategies, basic RAG, advanced RAG, everything revolves around the concept of vector similarity. So if you have two words, let's say cat and a dog, these two items, exist in the same semantic space. So that is what enables us to retrieve them in a single search result. But let's take another example. Let's say we want to connect Elon Musk and Tesla. So these two words, they are not textually similar, and they are definitely not vector similar. There's no semantic similarity between them. But we know that these two are very closely related. If you are, let's say, doing some research on various companies, Elon Musk and Tesla has to come up together in the same search result. So we know how exactly these two items relate to each other. Elon Musk is a CEO of Tesla. So this is called a relationship. Elon is and Tesla are entities, and this concept is what builds the foundation of GraphRAG retrieval system. So what we are going to do is we are going to take up one example of a knowledge system, and we are going to look into what tools enables us to do a GraphRAG retrieval, and we are going to run an actual demo to demonstrate that. So what exactly is GraphRAG? So basically, when you have your data represented in form of entities and relationship, not just plain chunks, that is where GraphRAG comes into picture. The data that you model has to be modeled in a way that the individual nodes or chunks are related to each other. And when you do a retrieval, what you are going to do instead of doing a vector search or similarity search, you are going to do a graph traversal. So this is how we do a GraphRAG ingestion and retrieval. So retrieval part is going to have a lot of complicated, reasoning. So for example, you have Elon Musk and you have Tesla. So you relate these two with the help of a relationship called is CEO of. So this is called a one-hop reasoning. Practical scenarios will have a lot of, complicated items where one node is connected to another node and then to another and so on. So when you want to do this kind of search, we are going to need specialized tools for storing the graph data as well as retrieving them. So that's what we are going to look into next. So as I said, we are going to store the data in graph form. So what do we store in graph form? We store the data which qualifies as a knowledge system. So if you have company data, you are going to have a certain kind of entities. Let's say a person, a company, city, and country. These are the entities that you need, and these are connected to each other. So this qualifies as something that you store in a graph system, and you can retrieve it with a graph traversal. So the basic constitution of a knowledge graph looks like this. You have entities which are very tangible items, a person, company, city, and country. First, you identify what entities you have in your knowledge system. Next, what you're going to do is, you're going to connect these entities with relation. So for example, a person relates to a company by the relationship of works at. A company is located in a country. A city has an office in a company. So, and a person lives in a city. So all these nodes are entities and all the edges of this graph are relationships. So this is how you create a graph. And the most important item after you build a graph using entity and relationship is going to annotate the entities with metadata. So for example, when you have a company, it will have a lot of supplementary data and metadata. For example, what space a company operates in, what is its revenue patterns, and so on. So this is something that you store as a key value pair in the nodes itself. And this is going to be very important in the graph retrieval, as we'll see later on. So the first question that would come to our mind is, if we do a graph traversal, do we throw vector search out of the window altogether? Well, not really. So in a typical production system, you're going to get the best of both worlds by creating a hybrid architecture. So what you do is when in the previous slide I defined, like in a node you define attributes which are linked to a node. So these attributes are going to be textual data. So what you can do is you can vectorize this textual data and store it as an additional key value pair in the node itself. So this is something that will enable us to do a hybrid search, which involves both GraphRAG as well as vector similarity. So that is how we are going to build our model and do our retrieval on. So to summarize, GraphRAG graph retrieval system enables the power of entity and relationship, and vector search enables us to do a semantic search. And when you combine this together, you are going to have a very accurate and sophisticated retrieval system when you're dealing with the knowledge system. So let's discuss on how the actual pipeline or architecture is going to look like for our hybrid GraphRAG architecture. So we can divide this in a couple of parts. The first part is going to be ingestion. So in RAG, what we used to do is we used to split up a document, which is your source of data, into multiple chunks. And you used to apply various chunking strategies. Over here, what you're going to do is we are going to run two parallel tracks in ingestion. We are going, first track is going to be vector embedding as usual. So the metadata we stored in the entities, that is going to be vectorized, and it will be stored in the graph node as a key value pair itself. And in parallel, we are going to create an actual graph using the entities and relationships that you identify. So once you're done with that, you have to combine these two. So you have a couple of options here. You can store the vector data in an actual vector DB, or you can store the vectorized data as metadata item in the node itself. So this is your choice and based on how you're going to structure your architecture. So once you're done with combining both this data, you're going to feed that into a graph DB. So we are going to look into how that graph DB is going to be structured later on. So the first part is ingestion. Once you are done with the ingestion and you have structured and modeled your data, obviously the next part is going to be retrieval. And it is going to be a dual retrieval because we are storing both graph and the vectors in our database. So just like ingestion, we are going to run parallel tracks for retrieval. One part is going to do vector and similarity search on the chunks which we vectorized earlier. And the second part is the graph retrieval, graph traversal. So these two are going to happen in parallel. Once you are done with these two items, you are going to combine them into one final search result. And during that part, you have to normalize the data, clear some noise, deduplicate the data and apply some re-ranking. And we will see that in detail later on. Once you're done with that, you're going to have some very filtered out results from your knowledge system. And this is something that you can feed into your GraphRAG, into the LLM system. And now you're going to get a very grounded and accurate answer from your search results. So let's deep dive into how the knowledge graph actually gets built. So the first and foremost thing that you have to do is you have to define how you are going to model your entities and relationships. So you have a couple of options here. First one is you define an upfront schema. So here you explicitly define the nodes that you identify as entities, and instruct LLM that these are the nodes that you need to take into account when you create a knowledge graph. And this is going to be the most usual thing that you do. And over here, there is no responsibility on the LLM to identify the nodes. You do it yourself and you make the schema very much rigid. Another option is offload and outsource everything about identifying nodes and relationship entirely to an LLM. And this is going to let the LLM traverse your data and build the relationship and the knowledge graph on its own. So once you have identified what is the schema that you are going to use, you start doing your data modeling for the GraphDB. And the first part of that is going to be entity extraction. So based on whatever approach you did earlier, if it is LLM, you are going to feed the data to LLM to identify the graph, or you are going to do it yourself. For example, if you are doing it yourself, the entities could be Elon Musk, who is a person, Tesla is an organization, CEO is the role, and you can even have dates as nodes. Once you're done, the next step is for you to identify the relationships between them. This can be also be done manually, just like you identified the nodes, or it can be fed into an LLM, and the LLM can connect the dots between various nodes. So once you're done with the entity extraction, next one is the relationship extraction. Now your knowledge graph is actually built. The skeleton is now built. The third one is going to be very important. It is a data cleaning part. So real world data is often messy. So for example, in your data, you might have references to Elon Musk, Tesla CEO. Basically, this can be identified as individual nodes, but actually this should be resolved to a single node. So this is where the data cleaning comes into picture. You merge your data, filter it, and make sure there are no duplicates. So you run the deduplication, and then you do a re-ranking, and after that, your data is completely ready for to be searched. And the final part, this is something that is going to enable hybrid search for us later on. So whatever data that you identified as part of entities, you're going to have metadata in that, and that metadata is going to be in text form. So you are going to run vectorization on that text and store that vector data as key value pair in your node itself. So now our graph is ready. And the next part is going to be how we are going to do a retrieval. So there are a few retrieval strategies you can employ when you are doing a graph traversal. The first and very basic one is an entity-centric one. So your questions are going to be very simple. So for example, the earlier example that I gave, Elon Musk and Tesla, this is a one-hop query. So Elon Musk is a CEO of Tesla. If your question is very simple like that, that is going to be come under the bucket of entity-centric search. So you identify a node and you expand to the first nearest neighbor of your node. And that is going to give you a good result. The second one is subgraph retrieval. So practically you are going to have a lot more relationship and that needs to be explored based on the user's query. So what you do over here is you don't just expand to the nearest node, you expand to the nearest subgraph. So whatever relevant nodes that you can identify based on the user's query, this you are going to filter out, and then you are going to get the result. So this is what we have referenced earlier as a multi-hop reasoning or extraction. And the third one is the hybrid search. This is what I referenced earlier. We are going to combine the power of both vector search as well as graph retrieval. And we are going to combine the results by merging and re-ranking. And that is going to give us a even more better result. And this is something that is more suitable for a production system. So the one of the question that will come to your mind is like, how are we going to represent this data? We know the nodes, we know the relationship. Where are we going to store it actually? So usually we store the data in a traditional IDMEMS DB. However, for graph-based data, traditional databases are not very suitable. You can model it, but it is going to be very clunky, and the queries that you write to retrieve that, they are going to be very verbose. So what you need to do is, in order to represent your data, you need to store them in an actual graph DB. So there are a lot of graph DBs in the market for a long time. So some of them are Neo4j, MemGraph, and Neptune. So Neo4j is the oldest and gold standard graph DB that has been in the market for a very long time. And MemGraph, Amazon Neptune, they are a few competitors that have come up recently. In these databases, you can store the data in form of entity and relationships instead of like what you would store in a traditional DB in form of tables. So once you are done with the storing of the data, the next part is the retrieval. So for retrieval, there is a very specialized query that you can run in a GraphDB, and it is called a cipher query language. And it is not SQL. It is having a very different kind of syntax, and with lesser amount of syntax, you can get better results. That is what a cipher query is. So because we have different kinds of databases, we are also going to have different dialects of the cipher query. So Neo4j has been around for a very long time, and it has revolutionized what we call the cipher query. And it is the most feature-rich version of the cipher query. However, as as graph databases started getting popularity, many competitors came into space, like memgraph and Neptune, and they are following open cipher based syntax, which is different from Neo4j. So that is what most of the competitors support at this point. And then because there are a lot of different query languages like Neo4j cipher and Open Cipher, the industry is actually trying to come up with the ISO standard. It is called GQL, and this is what all the graph DBs are converging towards currently. So we are going to look like how that syntax look like, but basically right now we have very disparate dialects in CQL, and this is how the schema differentiates between different kinds of graph queries. So for example, if you want to add a new node with classic cipher query, you use a create keyword. With the ISO GQL, you specify the insert keyword. Similarly, if you want to iterate through a lot of nodes, you with the classic cipher language, you use the unwind keyword. And when you want to do that in ISO GQL, you run a regular for loop syntax. So this is how there are a little bit of syntactic nuances between different dialects of CQL. So for our example that we are going to cover later on, we are going to use the classic CQL, and we are going to see how exactly the syntax of that looks like. So for example, the first thing that you need to do with graph DBs is you need to create a node, right? So this is the syntax that you use to do that. So you can see create is the instruction to create a node. Person is the node over here. You create a node of type person, and then in that you have name and age as the attributes. So this, and then you return the node. So this will create one node with the name Alice and age 30 as attributes, and the node is going to be of person type. So this is a very simple example. Let's say you want to create two nodes and also connect them with a relationship. So basically the syntax of creating a node is going to remain the same, but you also connect them with a relationship called works at. So this is how easily you can connect to different nodes. So this create syntax is equivalent to a insert syntax in regular SQL. Then once you have created the nodes, the next part is the retrieval. So for retrieval, you use the match keyword. So earlier we created a node of person of the by the name Alice. So when you want to search that node, you run that through the match query, define the node type, which is person, and optionally pass the one of the attributes of that node. This will give you a specific node which passes this criteria. If you just skip the attributes altogether, you are going to get the results of all the nodes of the type person. Then you can have other similar filtering that you used to have in regular SQL too, like where age is greater than 25. So this find syntax, this match syntax is equivalent to select syntax in regular SQL. So the reason we basically used CQL is because we need to do a lot of complicated graph-based retrieval, right? So when it comes to that, graph DBs give a very user-friendly syntax for you to work with. So let's say I want to find who Alice works for. So first I'm going to match a node of type person of the type of the name Alice, and then based on the relationship we defined earlier, works at, I'm going to match that with a company node. So with a simple syntax like this, I'm going to find the company for whom Alice works for. Now, let's say the next example is going to truly demonstrate how the power of graph-based retrieval. Let's say a person is a friend with someone else, and that person is also a friend with someone else. So this is a two-hop query. So you have a 2 degrees of separation over here. So in order to find that, all you have to do is specify friend star 2. So this, using this simple syntax, you are going to fetch all the nodes which are having a 2 degree of separation with the node that you started with. So this is where the power of cipher query language is truly demonstrable. And this is what is more suitable for doing a graph-based search in a GraphDB. So we are going to jump into an actual demo of GraphRAG. We are going to demonstrate one example of that with the movie dataset. So what we are going to do is we are going to explicitly define a few nodes of type of the movie dataset. And they are going to be movies, people, genres, studios, awards, and credits. Then what we are going to do is for every type of node, we are going to define metadata on them, and we are going to vectorize that and store it back and embed it in the node itself. Then we are going to build relationships based on these nodes. So for example, a person can act in a movie, a person can direct a movie. Then a movie can belong to a certain genre, movie can be produced by a certain studio. All these kind of relationships we are going to actually build and demonstrate some retrieval based on that. Once you are done with that, in the retrieval, we are going to do vector query, and that is going to do a hybrid search, vector search, graph search, and then a combined result based on both of them. So let's deep dive into the actual demo. So what we are going to do is we are going to take an explicitly defined schema in form of structured dictionaries. So over here, what I've done is I have defined a set of the items that are supposed to be stored in the data set. For example, in the movies data set, I have added a few popular movies like Inception, what year it is, what was the budget, what was the revenue. This will become the metadata that we store in the node at some point. So these are movies. Then we are having people node. People can be directors, actors, producers. They are going to have similar metadata about all of them. Then we have genres and as another node, sci-fi, thriller, actions. These are all different kinds of genres that a movie can be linked to. Then we are going to have studios as a node. So studios is the one who produces a movie that creates a good relation. Then we are going to have awards which are won by different movies. An award can be won by both movies and a director and an actor. So that's going to be another node. And then credits is what in credit links a person to a movie with a director or actor. So a person can act in a movie, a person can direct a movie. So credit is the relation that links those two. So over here we define the nodes. Now we are going to define the relationships. So the next relationship is the movie genre. Over here, we are going to link movie with a genre. So these are the IDs that we specified in the movie dataset and the genre dataset. So a single movie can belong to multiple genres. So we did that linking over here. So everything we are doing at this point is defining explicit schema and explicit relationship so that we can demonstrate a simple example in order to get the point across. So then you have movie studios. A movie can be linked to a studio. You can and then it can win a movie. A movie can win an award. A person can win an award. So this is another relationship. A movie can also influence another movie. For example, Tenet influenced Inception. So all these are the kind of relationships that we have defined. So the next thing what we are going to do is we are going to create a graph based on these entities and the relationship. Creating a knowledge graph is a time consuming process. So I have rebuilt that for the ease of demonstration right now. And what we are going to do is now jump into GraphRAG database. We are going to use memgraph as the GraphDB for the demo purpose. So let me show you how exactly the schema is going to look like based on the entities and relationships that we defined. So for example, movie is the central entity over here. So what do we store in the movie? We are going to store its ID, the title, year, budget, revenue, summary. And then taking all this together, we are going to vectorize this textual data. And then we are also going to store an embedding key and which will act as the vector search. So this will be an additional attribute that we store in the node, and this will help us do a hybrid search. So this is the movie node. So what relationship does a movie have? A movie can win an award. A movie can belong to a genre. A movie can be produced by a studio. A person can act in a movie, and both the person can direct in a movie. The person node has a self relationship too. A person can collaborate with another person. For example, an actor can collaborate with another actor or a director. So this is how different kinds of relationship has been created, and this is the common schema that we have derived based on that. Now let's dive into and visualize how this is going to look like when we visualize this data set in a graph form. So over here you can see we have a cipher query pre-built. So we are running the match keyword for finding all the nodes, and we are not doing any filtering. So all the nodes and all the relationship are going to be extracted. And when I run the query, let me just refresh this. Just give me a second. Okay, sorry about that. Okay, so this is how the graph is going to look like. So as you can see, we have a good amount of entities defined over here. So let's take example of a few items. So movie is the data set that is the node that we have, and it is this node represent in the interstellar as the movie. So this is related to a lot of neighboring nodes. So this movie has been has been produced by Paramount Pictures. So that is the relationship. Then this movie, Anne Hathaway, Matthew McConaughey, and other actors have acted in this movie. Michael Caine and Christopher Nolan has directed this movie. So all these relationships are built based on the data set that we have demonstrated earlier. So this is how it looks like. Now, what we are going to do is we are going to run a sample queries on this data set, and we are going to go from a simple query to a multi-hop query. So let's dive into that. So let's run a very simple query. I'm going to demonstrate a one hop query first. So what the question is going to be like, who acted in Inception, who directed Inception, and who are the actors in it. So this is going to do a hybrid search. Like I demonstrated earlier, we are going to first run the query embeddings on the metadata. Then we are going to do a vector search on the movies. And then we are going to expand the movie context to 2 degrees of depth. And then we are going to do a vector search on people, because movie and people are the two nodes that we have identified in this query. And same way, we do a vector search on movie, and we do a graph traversal on a person with the depth as a 2. So this is going to be doing a one hop retrieval. So the answer we get is directed. The Inception movie is directed by Christopher Nolan, and this is the cast that we have. So what this demonstrates is a movie has been directed by a person, and a person has acted in a movie. So we have two nodes and two relationships. So this is a one hop query. Now let's take a little bit more complicated query, which will demonstrate a two hop query. So I'm going to ask which other movies share genres with Dune. So what the system needs to do is first find what is the genre that belongs to Dune, then expand to other movies which also has the same genre. So that for that we are going to do a similar search. We do a query embedding, then we do a graph traversal on all the identified nodes, and then we are going to combine them, and this is going to give me an answer. So so basically, the movie Dune, it is having a sci-fi as the main theme. So it also identified another movies which is having similar, genres like Tenet, Blade Runner, Mad Max. So this has three entities involved: movie, genre, and another one is person. So a movie can belong. So we have two similar nodes, but they are linked differently. So one movie can belong to a genre, and then another movie can belong to the same genre. So this demonstrate a multiple hop query. Now we are going to move into what will truly demonstrate the multi-hop query. We are going to take a very complicated query over here. So uh, what I've asked is what studios produced movies directed by multiple award-winning directors. So there has to be a movie which is directed by directors, and that director has to have won multiple awards. So it has multiple entities and multiple relationships. So as you can see, we are going to do a similar vector search and graph traversal, and it gave me a result of a few movies like this. Legendary Pictures, Paramount Pictures has 4 movies like that. Sony Pictures has 6 movies like that, in which the directors of those movies won multiple awards. So this is true multi-hop query. So this basically is what GraphRAG is about. We are going to have a lot of relationship which are going to be extracted from your query. Then you narrow down the results by doing both vector search and graphs retrieval search. Then you are going to combine the result and get a very grounded answer. So as every technology, GraphRAG is also not without its limitations. So the first limitation we have with it is having a very high operational overhead. So the tooling that we create with GraphRAG, the relationship and entities that we define, there is a huge role of LLM in every step of this procedure, both in ingestion as well as retrieval. So it is heavy on the computation side. It is not that fast, and then it is going to have a very high token consumption. The tech stack is that we are going to use is not usual. You have to use one of the graph DBs. So that's one of other complexity. And then the most important one is if your system is having a lot of frequent data updates, then you are going to have to rebalance your graph every time a new node gets added, because a new node can belong to multiple other nodes. So you have to recluster your entire database, the graph DB, in order to make the data coherent. So that is one of the biggest limitation over here. And another part is the graph schema sensitivity. So depending on how you define your schema, your queries are going to be very sensitive to it. So if you define a very rigid schema in which there are very few nodes, then the nodes or relationship which haven't been identified at the building step, that is not never going to be reflected in the search results. And let's say you create a very loose schema. You create a lot of nodes and every node is connected to every other node. Then it will create a graph which will look like a hairball, and that is not going to give very good results because the LLM will have to go through every node, and it will increase the chance of hallucination. So these are a few limitations also that you have to take into account when you decide whether you want to employ GraphRAG as a technique instead of a traditional RAG. So to summarize, let's just take a quick comparison of what traditional RAG excels at and where you need GraphRAG. So to start with, when you want a very specific fact-based retrieval, you generally want to go with traditional RAG when you don't have a lot of relationships, because and it is the question is like needle in a haystack. Because vector retrieval is going to be very good at identify the vector semantic space, traditional RAG is going to excel at that. Then let's say you have performance constraints. So you need to have very fast retrieval, and your budget is also very limited. The GraphRAG is typically very high on the token consumption. So in this kind of cases, simple cases, you need traditional RAG. Then, so one of the point that I already covered, if you want to have very frequent data updates, with traditional RAG, it is just another record in the database table. With GraphRAG, you need to recluster and rebalance your entire DB. So that is not suitable for GraphRAG. Traditional RAG excels at that. And then let's say you have very similar, documents that you want to search on. For example, the company leave document that Krunal covered earlier. So when you have very simple documents, traditional RAG is going to be the best for you. Now, when GraphRAG is going to excel is, as already explained earlier, you're going to have a lot of relationship between your chunks, not just regular chunks. And you want to explore hidden relationship with multi-hop queries. That is where GraphRAG actually excels. So entity A relates to entity B and then to entity C, and you can expand your subgraph as much as possible depending on the complexity of the query. This is where GraphRAG is going to give you good results. So basically, this GraphRAG is going to be suitable for very high complexity domains. For example, you are doing some scientific research or some detective research in which you have to connect a lot of dots. In this case, the modeling overhead that you need with GraphRAG is actually going to pay off. So that's where GraphRAG is going to be a better choice for you instead of a traditional RAG. And you can always combine vector search and graph search as we did and create a balanced production system. So going back to the initial, context that we set earlier in this presentation, is RAG dead? Well, not really. It is pretty much prevalent in the production systems. You just have to identify the right use case and employ the right RAG technique or a hybrid technique, depending on your use case or the query complexity that you anticipate. The examples that I gave you before for the GraphRAG, So Elon Musk is a CEO of Tesla. So you can still achieve that with traditional RAG. Let's say in Elon Musk node, the chunk that describes Elon Musk, you add lot of metadata. Let he works at Tesla. He's a CEO of Tesla. So this is going to be picked up by vector search. So it's not that it is not going to work, but the problem is you have to anticipate every kind of user queries that comes your way. And you have to model your relationship in a traditional RAG by stuffing a lot of text in your documents. And that is not a scalable approach. So that is why when you have relationships, GraphRAG is the way to go. So as always, just like traditional RAG and GraphRAG, the industry is rapidly evolving. So there is another concept which is called agentic RAG. Both traditional RAG and GraphRAG have their limitations. So the next evolution of this RAG techniques is going to be agentic RAG. And that is something that we are going to cover in our next meetup, where I'll hope to see you all again. Thank you, everyone. We'll just open up floors for questions.
Yes.
We have actually. So we have not used RAG retrieval, but we have used creating a RAG based on different techniques.
Can you share your use case? What use case for this is for?
So the actual use case that we used in production systems. Yeah. So I'm going to just give you a high level overview on what actually we did. So we had a lot of documents, and the documents had certain techniques that needed to be applied to a certain user in a certain chatbot. So the techniques were having a relationship. You apply first technique and then another technique based on what works for a user and what doesn't. And because of these techniques are very much related and there is a sequence in them, we employed a graph, retrieval graph database to it. And when the user actually chatted with our system, we did a real-time, lookup with a graph traversal and pulled up the right technique.
And how did you evaluate the results?
So we have evals for that. Like we implement evals, and evals are the way that you want to evaluate the answers of your RAG system. And even for the GraphRAG also, we are doing a research like how we can do the evaluation. But we do have frameworks defined that we use to evaluate the answers.
Okay. And going to the traditional RAG systems, did you implement it anywhere?
Yeah, we
In
have an
production?
internal product.
So what were the major limitations you faced and how did you resolve that?
So whatever advanced topic that we covered, those are the learning lessons from our internal implementation. And when we started that, we also faced some challenges, and that's how we overcome those challenges using this advanced techniques. So those techniques are in place in our internal RAG product.
Okay, thank you.
Okay. First of all, thank you for covering. Actually, you covered pretty much detail about the RAG and GraphRAG both. Okay, so yeah, it will be very useful. Now, yeah, my question is actually, you mentioned right in the productions or real life scenarios, we need to merge both the thing RAG and GraphRAG, RAG. So can you give us such a use cases where both will be the needed and how that can be implemented?
So basically, when we go to GraphRag, semantic similarity just doesn't go out of the window. You still you will when the user chats with your system, they are going to have all kinds of questions. Some of them are going to be very targeted to the relationship which exists between different entities. Some of them are going to be generic, right? The user doesn't know what kind of retrieval system we have in the backend. The question that they are going to give is going to range from all the use cases that ranges from traditional RAG to the graph RAG. So what the hybrid system that we are going to create, it is going to create a parallel retrieval, and whatever is the best among that, we are going to decide at the merging and re-ranking stage. That is how the result is going to be given to the user. So the answer of the question is we don't anticipate every question the user have. We identify the broader use case in which the graph rag is going to be give lot more accurate results, but that doesn't mean the vector search based questions is never going to come. So let's say the user is having a question in which pure vector search will do, then you entirely skip the graph retrieval. You can just narrow down the nodes in your graph because in the graph you already have metadata, right? So you just identify the nodes and then just respond to your user based on that result.
And I would like to add something more on top of it. Like, let's say, for example, majority of the use cases you can start with RAG, but if you are working in a domain like pharma or judiciary, where the connection is very important, so you can consider starting with GraphRAG in that case. Otherwise, you start with traditional RAG. You see if you are facing the issues around the user's queries in traditional RAG, then you can opt for the GraphRAG. So it's always an evaluation that you will have to do from step 1 to step 2.
So now on the merging, it will be on our systems, or we need to create, or there is any technology available for that, where merging or the flow divergence will be on the RAG to GraphRAG.
No, it is going to be our system. So when we merge, we also re-rank. The re-ranking system, Kunal demonstrated with the Cohere ranking model, right? So whatever result we get as part of the hybrid search, the vector search and the GraphRAG, that is going to be now another input that we are going to perform on the same steps that we did on traditional RAG. So the merging is going to be simply you stuff all the data you get together with vector search and GraphRAG, then you re-rank with Cohere, then all of this data goes into the LLM as an actual query from our side. Exactly. Yeah. A mini graph RAG pipeline, if you might.
Yes. So basically, you mentioned about GraphRAG. So how did you implement that ingestion pipeline? So how did you process all the documents to ingest that into the RAG GraphRAG? So that wasn't the part did not covered in that scenario. The
Yeah.
flow you mentioned in there.
So with GraphRAG, typical GraphRAG scenario, is a little more complicated when you take up an actual document, you split the text and then define the relationships based on them. For the demo purpose, what we did is we created a structured, data of movie data set, and which we would have created by extracting that data from a certain documents. So that particular part was not very much in scope of what we wanted to demonstrate here. But basically, it is a similar, process that you are going to follow. You're going to chunk the results and mark every chunk as a candidate node. So after that, you feed the chunk into the LLM, and or you define based on your, a business requirement whether that chunk qualifies as a node, or you just add it as a metadata. So that's just a pre-processing step that you have to do before you actually start the actual GraphRAG build process.
Any other question? No?
Can we store vectors in GraphDB, as you mentioned?
Yeah. So in the example that I demonstrated, we actually had every node is just a collection of key value pairs. So for a movie, we stored title, produced at, what movie awards it won. So along with that, another key value item is, whatever metadata you had earlier, you vectorize that and add it as an embedding key in the same node.
I see. Also, you mentioned that the GraphDB also needs reclustering of the data that get processed. So if something changes on the document, then we need to recluster it. So how much time does it take, and how much compute power does it take?
It depends on the volume of your data. So if you have 100 nodes, it's going to be very instant. If you are working on the some very complex domain, like I covered, like scientific research, detective work, where you have thousands and thousands of documents, that's going to be take up quite a bit of time.
So it does it matter on the changed data sets? So changed nodes or all of the nodes?
It will apply to all of the nodes. So let's say in the example that we covered, we took a movie data set, right? Now let's say I have forgot to add one director in the director entity. So if I add that, I have to check what are the existing movies in my existing data set, and if that director also collaborated with that movie. Or let's say you add another actor that I missed. That would be a better example. If I add an actor that I missed in my data set, I have to check in my existing GraphDB, do they have any movies that they already acted in? So then every node in that existing DB becomes a candidate to be linked to the new node that we add. So the GraphRAG basically is more suitable when you have very infrequent updates that you want to make, or the updates are very worth it because the kind of work that you want to do, that overhead pays off.